introduction with LS Dyna. Myself, I work at Rand on our structural side of our business, so I do a lot of simulation with an Ansys mechanical package as well as with LS Dyna. So one for more implicit, one for the explicit applications. So today, I want to give an introduction for the Dyna package, right? The primary agenda really is I have three things I'll go over with you. One is a quick overview of the Dyna capability, just show you what it can do in general. Second is I will go over a quick general workflow using an example, a very simple example problem. Sort of, letting you guys, especially if you haven't touched the software before, to get a sense of what you have to do to be able to, say, for example, trial the tool to see if you can use it to help your business or help with your personal development, right? What does it take to set up a model? What are the things you need to consider? And the third thing is I'm going to talk about some very general, simple applications, right? The third part really is to let you see just the amount of potential application that the Dyna package can be used to simulate. Basically, it's a physics-based tool that can be used in a much wider range of applications than a single code that you have in other packages, which is really, in my opinion, one of the most defining characteristic for this FEA code, right? And it's also why it's honestly one of my favorite. I personally really love it because of its truly wide range of capabilities. Okay, my target audience really, like, it would be really good if you guys have done some FEA in the past, right? But even if you haven't, like, this is not a overly technical presentations. It's truly an introduction, but I'm not gonna go into a lot of really simple detailed explanation for specific terms. I'm sort of assuming that you have some understanding of that. But it's, even if you don't, it's okay. It's not a big deal. Okay. All right, let's get started. So Dyna, right, really is known for explicit dynamics, right? So when you hear the term here, really just means highly transient, highly deformable, highly nonlinear physical phenomena, right? So for example, this is a very well-known, recently published Lego crash animation, right? On the left-hand side, it's a actual physical test with these Lego build cards. On the right-hand side, it's a simulation environment, right? So you can sort of see the amount of detail the package is able to pick up. And Dyna is very well known. It's honestly one of the only two that's used for crash, right? So if you want to do crash simulation, like you just want to crash car in your career, there are certainly folks out there doing that. This is really one of the only tools out there that people are using. It's certainly the market leader, right? 17 out of 20 top auto companies are using this. And in terms of speed, which, as far as a program goes, right, it's one of the defining things that makes it better or worse is how quick can it go, and it's highly it's extremely fast in terms of its parallel processing capability, which means, as you invest in hardware, the model runs faster and faster. It scales much better with hardware investment. Okay, so once you look at a very, in terms of crash, right? So I could actually take a truck model from the open source resources online and then crash it against a post, right? Just for the sake of demonstrations, right? We can also take two cars, align in some orientation and crash them against each other, and you can sort of see these detailed deformation around the bumper or all the stuff inside underneath your hood, right? And a lot of people are doing this type of work, right, for their employer, for their organizations, in terms of applications that I obviously won't go into, right? This is a very specialized world, and it's very much what Dyna is known for, right? But and then one of the things, before I go into that, one of the things is that if you are a purchaser of LS Dyna, you are going to have access to these baseline model. These are the vehicle models. This is the tire model. This is a human body model. This is what's called a barrier model, right? So you can actually get access to these baseline models. And basically, say, for example, if you are one of the guys that are designing a barrier, right, you can take one of the vehicle model and just run against your own barriers. So these are the things that people have created in the Dyna community to allow you access to these, which helps you with your organization if your goal is to do, say, crash and occupant safety and so on and so forth, right? But as I was saying, Dyna really is about much more than just explicit dynamics. I think in a lot of ways, if you look at the true range of capability inside Dyna, it's also extremely powerful in the implicit side, right? So for example, if you want to do analysis that's highly nonlinear, right, which means you're going to see a lot of deformations, but also in which the duration of the physical event is extremely long, right? In those cases, right, if you're familiar with the simulation world, right, that's not really suited for explicit because the duration of the physical event is so long, even though you have a highly nonlinear event, right? In a lot of those cases, right, Dyna is also extremely well suited for those type of problems. You can also do thermal problems, do electromagnetics problems. You can do NVH, like modal analysis, do response spectrum. You can do things like forming, right? You can also do, say, for example, some CFD problems, right? There are also things within the particle, within the element-free method, which I'm actually going to demonstrate today, right? That allows you to handle problems in which the deformation is extremely large, in which a Lagrangian method is no longer the most suited for it, right? So in terms of the capability within the code that you'll be getting, right, it's so much more than what it's mostly known for, right? That's the first thing to know. And the second thing to know really is that it's not just a structural solver, right? And I sort of hinted at that earlier, right? It's also a multi-physics solver, right? So what that means is that you can do a fluid and structural interaction, which is a simulation that involve both structural analysis as well as CFD analysis, right? And then you can also do a combination of any of the other multi-physics problem that you can sort of imagine, right? So if you've ever done FSI problems, like fluid structural interaction problems, right? Usually it requires the program to talk to each other in between steps, right? In between your simulation steps. And that you have to check for convergence for that data transfer. And that's the type of thing that's no longer truly necessary within within LS Dyna, because you are solving the problem within a single code as opposed to having to use two different programs to do it, right? So these are things that are very, very unique to Dyna, but obviously it's sort of for more advanced users. But knowing that capacity, right, really help us appreciate just what the program can do, right? Okay, so here's some very quick example, right, of this is a fuel tank sloshing, which has a impactor coming from the right-hand side. Once it impacts it, you can sort of see how the fuel start to behave inside the tank. So this is like a typical sloshing problem. This is the Orion crew module hitting against the floor, which is made of water, right? This is a pouch which has sort of fluid filling into it. This is a ballistic problem, which is penetrating a ballistic gel, right? So these are the type of thing that in my mind is much more multi-physics, right? Even though not all of these are done with a multi-physics solver, right? Some of this are done with the element-free method, which we'll talk a little bit today, hopefully, right? But knowing these capability, right? These are things that is really, sort of explains the type of things that you can expect to do inside Dyna, which usually requires, more than just a structural package sometimes, right? Okay, so let's look at the basic workflow. All right. Dyna, like any other package, right? Really, you have three components. You have the pre-processing, you have your post-processing, and then you have your solver itself, right? So when you buy the software, right, and this is one of the confusing things that I've often heard, right, is when you buy the LS Dyna product, what you're buying is not a pre-processor or a post-processor. What you're buying is the solver itself, which means it require an input deck to generate a bunch of data, a bunch of files, which is going to be read by another program, right? So a pre-processor is what's going to create an input deck. An input deck is fed into the solver, which is what you're buying. And then when the program finish executing, it's going to generate a bunch of files, which is read by a post processor, right? And that's the essence of of a workflow per se, right? So when you're buying this, remember you're first of all buying the solver. Then you have to decide what is the pre-processor that you're going to be using and what is the post-processor that you're going to be using, right? So industry has currently a few pretty standard pre-processor and post-processor that they're using, right? So Hypermesh and VMAP are two packages that are not an Ansys product, right? These are product outside Ansys that a lot of people are using out there, right? You use Hypermesh to pre-process, and you use Hyperview to post-process, and VMAC has both the pre-processing and post-processing capabilities. Now, LS Prep Post is a free software that anybody can download, right? Even if you don't own the product, you can download LS Prep Post, which allows you to basically build a model, right? And it also allows you to read the data that's generated by the solver after you feed it an input deck, right? But obviously, without the solver, it doesn't really do anything because you can't solve anything. Even that's why it's free. But LS Post being a free processor and post-processing tool, right, is essentially what's created by LSTC. And this is the tool that's sort of like, if you don't want to use any of the other ones, you can use this. One of the downsides with LS Post is that it's mildly difficult to use, right? So it certainly has a much steeper learning curve. Like I myself do not use it for pre-processing. I use it for post-processing because for pre-processing, I think there are just better ways to do it. That's much less convoluted, and it's also has a stronger association with your CAD interface, right? Which makes it less ideal for myself, right? So Ransom being an Ansys house, what we use is what's called the Workbench LS Dyna. So when Ansys purchased the creator of LS Dyna, which is LSTC, right? So they started creating this pre and post processor called a Workbench LS Dyna, which is this thing that you can insert into your Workbench. So hopefully most of you guys have used the tool in Ansys, right? So you can drag and drop something like this into your Workbench, right? And that's essentially what's called the Workbench LS Dyna, right? It has your geometry prep tool in your model, similar to any Ansys mechanical model. And this is a tool that's very much similar to a typical Ansys preprocessor, right? But its goal is to create the input deck, which is going to be read by the solver, and it also has capability to post-process information that's being written by the solver, right? So this is, in my opinion, going to be the future, and then for no other reason than the fact that because Ansys is creating this, right? So because LSCC is now Ansys product, this is going to be a dominant preprocessor in the future because Ansys is going to make it better and better and better and suited for our customers. So keep in mind, right? So I'm gonna do a demo today using this in a little bit, right? And you guys can sort of see what that will look like, okay? And in my opinion, this is a very easy to use tool. Certainly with things that you have to get used to, but it's going to become better and better in the future. Okay, so what is the essence of the Dyna workflow, right? And I think you can go through a demonstration of the tool and so on and so forth, but really the only thing that you have to take away is that any object, which means like in this case I have a contact object that's created inside Workbench Dyna, right? I have an edge contacting I have a bonded contact between an edge and a surface between two tubes, right? Two square tubes. And then I'm going to bond them together, right? That's an object that you're creating in your model, right? Anybody can do that, pretty easy to do. But what is actually happening, right, is when you're creating an object like this inside Dyna, what's actually happening is a key card that's generated look like this. This thing is what's going to be recognized by your input deck, by your solver, right, by the Dyna solver. All of these little things that you're seeing here in this presentation, we won't go through them, what they mean, all that stuff, right? But basically, these are the individual parameters that defines what the contact is supposed to do, right? So if you think about a bonded contact, what are the parameters of a bonded contact? These are the things that you are going to have to indicate in your GUI, right, in your graphic user interface, which is going to allow you to define what the card look like, which is going to tell the solver what to do with that specific contact object. Okay, that's the essence of it, right? So really, when you're building a Dyna model, you're essentially constructing a set of cards that's going to be recognized by the program to generate a set of response information for you to read in your post-processing tool, right? So when you look at a contact card like this, right? I chose a contact card because it's actually the more complicated one, right? A contact card will have the name of it right here, right? You will have what's called a mandatory cards, which means every single contact card, doesn't matter if it's a bonded contact or a frictional contact, gonna have a set of command parameters that you have to input. These are the mandatory cards. You also have what's called optional cards. These optional cards is gonna define things like contact methods. It's gonna define amount of penetration allowed, and so on and so forth, right? There's a lot of different things, right? Each of these little parameter right here, you can actually go read about them to see what they're trying to do. Obviously, I won't talk about them, right? But here, what we have is what's called a tied nodes to surface. So if you can read this text right here, right? This underscore is what tells the computer what is trying to look for, right? So tied means it's bonded. Nodes to surface means we're tying a bunch of nodes to a segment, which is called a surface. Okay, and that's the clue you can sort of get what is Dyna trying to do with these cards. Now remember, all you have to do is to input things into a GUI, right? It's gonna pump a card out, and then you're gonna have to make sure the card is right by changing the GUI to make sure you get the right card. And that's the entire process for correctly building an LS Dyna model is you need to understand how is your preprocessor interacting, is behaving to generate the cards, and what kind of behavior is being indicated by the model that you're setting up, right? And that's the really the nature of the process of learning how to correctly set up an LS Dyna model, right? And of course, you need to do it for every single object in your model. Could be a little, in the beginning, it could be a little difficult, but once you learn it, it becomes easier and easier to do, right? And this is the basic scheme for a contact card, right? So you can sort of see there's an option 1, which is the first keyword. It's gonna tell you what is the type. And then the 4th keyword is gonna tell you the offset options, right? So all we didn't have option 2, we didn't have option 3 because we skipped them because it's not a thermal pair, right? We also didn't need ID. So that gives you an idea. And then for every single card, you're going to have some kind of syntax, just like a programming language in a way that you need to sort of understand. You learn it slowly, right? But once you learn it once, you realize it gets easier and easier and easier to understand. Okay. Now, so why is this a good thing, right? So some people might say, I really don't like to look at these code. And as I mentioned, I think, in the beginning, it might look like something like a hurdle you want to overcome. But once you overcome it once, it gets easier and easier and easier to understand. And the second reason it's a good process is because, if you ever think about how do you know the model you're setting up is correct, right? You want to look at the components of that model, right? If the components of that model is all individually set up correctly, you have a good model, right? But how do you know the individual component is set up correctly? You look at the key cards. If you know the key cards is being created in a way that corresponds to the design intent, right? For example, if I have a bonded contact, do I need to define at what point does the bonded contact break? That type of thing, right? If I wanted to define something like that, I can do that. And that kind of behavior is what's defined in the key card, right? So when you want to generate a good model, you have to make sure the individual components are captured. And within the component, we want to make sure the key card corresponds to how we want that component to behave, right? For example, material, for example, contact, for example, boundary conditions, right? Any of these things can be individually looked into to make sure you are generating the correct input deck, right? Correct a key card. And that's the nature of a first principle decomposition of a difficult model into components that you can investigate and study. And that, in my opinion, is why this system actually works really well once you really get used to it, right? Okay, so let's look at a quick example, right? I'm not gonna talk too much about cards, right? But what I wanted to do with this example is to show you how I will set it up inside Workbench Dyna. I'm not gonna do a demo here because we're limited on time, right? But I'm gonna show you what the model look like. And I'm gonna talk to you a little bit about how I think about setting up something pretty simple, right? So this model is essentially like a rubber ball, right? So this ball right here is a shell body. I know I'm not really showing that. It's gonna have some kind of air pressure inside it, which I'm gonna define. I'm gonna drop this ball 2 meters from the ground, right? Which is right here. This is the ground, and I'm gonna have a drop height defined, which is gonna translate to some kind of impact velocity. So as you can imagine, if it's a rubber ball hitting the ground, it's gonna compress into a smaller volume, then bounce back, right? That's a pretty simple example. It's also an example involve an airbag model. It's also an example that's the basis of any drop study they will do, right? But it's a very simple example. But if I show you quickly what the Workbench Dyna model look like, this is pretty much it, right? So I have some component being imported. I have a corner system created, right? I have a bunch of name selection created. So if you're familiar with this interface, that's essentially what I did, right? A couple name selections, a corner systems, a bunch of body being imported from CAD. I have a couple material model being written into the input deck, into the preprocessor. And then I have a few airbag model, right? And then I have a gravity inserted, and then I have a rigid wall, which is acting like a ground. And that's in essence what I did. And then in the presentation side, I'm gonna show you guys sort of a step-by-step what I'm doing and what I was thinking about when I created it, right? Because I think that's the nature of that's really what's important, right? And even for something this simple, okay? So if we look at, first step, right, I'm going to import the geometry. So when I import the geometry, this is the shell body. I'm going to define the shell thickness, which in this case is 15 millimeters, right? As you can see, this is a 15 millimeter shell. All these body are being meshed with the shell element with a 15 millimeter thickness, right? So I have 5 different balls. The reason I have 5 different balls is because I want to change the air pressure between them to show you what happens. So you can sort of think about in your head now what's going to happen if the pressure is higher versus lower. Think of basketball, right? Which one is easier to dribble if you have a higher pressure basketball or lower one? Now, when I import a geometry, right, what's happening in the input deck side is I have a part card being generated. I have a section card being generated. The part card just tells you the program what is the part number, right? And then you have these two things which called a section ID and a mat ID. So material and section. Section is right here. Section defines, like, for example, things like element formulation and shell thickness. Obviously, I'm not going to go too much into it, but knowing that these things are what's happening in the background as you just import a geometry and mesh it. Okay. And of course, there are nodes and element stuff that's not showing on the screen. Just know that they exist. They get written into like a text file, right? And then next is I'm going to define the material of my ball, right? I want the ball to be made of some kind of rubber, right? So I have a dummy rubber material, right? A Mooney-Rivlin material model for rubber. I'm gonna use it. This is the basic information. So even though I have a structural steel being defined in my geometry, I override it with a text file with a keyword snippet in Dyna, which is gonna override the material with the Mooney-Rivlin rubber, right? All I did here is I'm telling the program what kind of material model I want to use for my ball, right? For my shell, for my ball material, ball body. And in this case, this is also what's happening in the input deck. I basically inserted this card into my input deck, right? And then I'm gonna insert a coordinate system. Basically tell me I want to tell the program what's the orientation of my drop, right? In this case, that's why I have that coordinate system. So you see, I have a global one, I have a local one. So I now have a defined coordinate system card in here. I have a local coordinate system card in here, right? So what I'm doing really is, for every single object I insert into my preprocessor, I start thinking about what's the corresponding key card that's being created, and how do I make sure it's done correctly, right? So it's really not a program in which you can follow a set of instructions every single time and you will do it correctly every single time, right? It's not there yet. Maybe I should say, right? But it's also not what you want, because you want to control the behavior of your model, especially when the model gets complicated. Okay, so the mentality that we want to have as a simulation engineer doing Dyna work, right, is to really get into the understanding is what are we doing in the preprocessor and how does it correspond to the input deck. That's the mentality that you want to get into, and which is what I'm demonstrating today. Okay, and next I'm going to generate a bunch of name selections, each scoping to the body of the ball. I have 5 different balls. And you notice now I have a selection ID here, right? So why did I do this? The reason I did this is so that I can tell the later step of the model to use these ID to do something with it, right? So for example, so what happens when I generate name selection inside Workbench LS Dyna? I'm creating these set part cards, which is going to scope that body into a set. Now, the idea of a set is that you can call on it, and then you can then do something with it, right? That's the idea of like a set, right? So now I have 5 different body with 5 different set ID, and these are just essentially parts that are becoming part of a set, right? So why did I do that? I'm gonna create an airbag model for each of my 5 balls, right? So for example, when I create an airbag model inside Workbench LS Dyna, I'm gonna scope to the name selection, right? And then correspondingly, it's going to create a key card inside the input deck called airbag simple pressure volume. Now this might not mean much to you, right? And I put in some information, so as you receive this in the future, if you want to look at what each of these parameter means, you can look at it. But basically, the idea here is that I'm gonna have to tell the program what's the amount of pressure I should have inside my ball at t equal to 0, right? Before it hits the ground, what's the inflation pressure of that ball? With a very simple airbag model, you don't have any leak, right? You don't have any temperature increase as the volume decreases, right? As the pressure increases. Things like this doesn't exist for a simple airbag model. All I'm gonna do is I'm gonna correlate the relationship between my pressure and my volume based on a single parameter called a Cn. This Cn parameter right here is this number right here. And then, without getting too much into the math, right? This is a pretty simple algebraic math. Essentially, as you increase the value of your Cn number, right, as you increase the value of what's in the tabulated data here, right, this value, right, as you increase this value, you are going to make the number, make the pressure in the airbag bigger as the volume decreases, right? Which means it's a way to represent inflation pressure without directly indicating what that is, right? So it's a relative term based on the size of the ball, and that's the essence of what it is, right? So as I change the Cn number from right to left, right, you can sort of imagine the inflation pressure gets higher and higher and higher even though I didn't specifically calculate what it is. I can show that in post-processing. And mostly for the purpose of this demonstration, I'm just showing that as in a sense of just increasing it, what happens, right? That's my goal. Okay, so next thing we want to do in step 6, right, is that if you look at an object called dynamic relaxation, which is what I created next, right? Dynamic relaxation is essentially a way of generating what's called a preload, right? So why is that necessary here? Is because before the ball impact the floor, I'm gonna have to tell the program to inflate the ball, right? And that has effects that we have to understand. So because you are introducing load into the system, right? In a dynamic analysis, things start vibrating. So we want to make sure before we start the analysis, right, we're minimizing the kinetic energy in the entire system. And then the nature of a dynamic relaxation, right, is essentially a way to preload your entire model in an explicit sense, right, until your kinetic energy goes to a very low amount. So all that really means is that you're just preloading the structure until you don't have a lot of ringing in your system, right? Your ball isn't just ringing around before it starts analysis, and that's really what it is. Right? It's a form of preload. Remember, this is an object I inserted into my preprocessor. So what is it actually doing? What's most important? What is the card that's being generated? Which I guess I actually didn't show. What's the card that's actually generated in the input deck? But basically, what it is that it's telling you to preload until some threshold is hit. Okay. So in this step, I do a preload. Once I do a preload, right, I'm gonna have to define a floor, which is what ball is gonna hit, right? And that's essentially what this rigid wall is. This rigid wall basically is a planar wall with some coordinates that you're gonna find in space, right? And it look like this, right? So you see there's a floor right beneath my ball, right? And it's gonna contact every single body in the model, and that's really what the rigid wall is. You don't have to define a contact pair with a rigid wall. It will just do the contact for you. That's part of the behavior of this card, is that it creates a floor that you can sort of see in your preprocessor, and the ball, while already being inflated in the preload step, is going to hit the floor and bounce back, right? And that's truly, for the most part, the entire model, right? In a quick way, I've explained both what I did and what I was thinking about, right? And then lastly, I guess I should talk about is the control cards. Control cards are basically just global level control that you want to implement into your model. So if you're familiar with the explicit dynamics, right? So for example, mass scaling is something that can increase the runtime of your explicit analysis. In this case, I just set it to no, and that's a global control that you can set in your termination. Control termination essentially controls that. You can also do global contact control, global hourglass energy control, and so on and so forth, right? So we won't go into much of that, but these control cards are a global level, a way in a global level that you can control the behavior of your model, right? So for example, for every single contact, you want to contact behave in a specific way, you can generate a contact control setting such that it does what it does. Okay. We don't need to go into too much of detail. This is something that once you dig into the program, certainly you want to study up on, right? And then lastly, how do you submit a job, right? So once the model is set up, right, there are 3 different ways you can submit a job. The first way is what's called LS run. So if you go to your Windows bar, if you have the program, go to your Windows bar, you search for LS run, right? LS run is going to ask you to point it to the location of your input deck, right, which is the first line, and then it's going to ask you to point to the location of the solver, which, by the way, is that single executable file that you spend a lot of money buying for, right? That's essentially the solver, which is you're pointing to. And you're going to define how many core you're going to use. You're going to define the memory requirements, which is usually calculated for you, right? And then that's going to allow you to submit the job, right? Now, what this thing requires is that you have to write out the input deck, which in the case here is that you basically just go to here, and then you just go to your LS Dyna, and then just do the environment, and then write input deck right here, right? That's what is going to allow you to write out the input deck, and that's what the LS run program needs. You can also do it directly inside Workbench LS Dyna by just clicking solve, right? That also works. It does pretty much the same thing in the background. With some limitation that I've run into, my personal preference is to use a third way, which is using a command line interface, which is very similar to LS run. It really does exactly the same thing, except instead of using a program to write the script, I just write it myself. It's really not that different from LS run. It's really exactly the same. I just write. You see this expression right here? I just write out that expression myself inside a script, which is going to allow me to submit my jobs. Or I will define where to find the input deck and where to find the solver and so on and so forth. Okay. And so you can sort of see, right, the way to submit a job in Dyna, you basically just tell the solver where is the input deck, and that's it. That allows you to submit a job to the solver, and then he's gonna generate a bunch of files for you to read inside the same folder where your input deck is located, right? That's your working directory. Okay. And then when you solve it, you're gonna see text file that look like this, right? So you have a dynamic relaxation, and then you're gonna give you a bunch of text file, right? And then if you look at the actual explicit model, it's gonna give you the t equal to 1, and the cycle 250, cycle 5,000. And this right here is your stable time increment. If you're familiar with that, that's basically is how quickly your simulation is running. And that's defined based on the size of your element, based on the modulus, and based on the density of your material, right? So you can actually look at what that would be by inserting a CFL time step in your preprocessor, right? And this object right here lets you see what is the smallest time step in your model, and that gets scaled down by 0.9 by this TSS factor, right? But basically, which is why this number right here, 1.67 to the negative 6, is a little bit smaller than this number. But the idea behind it is that this is what you will see when you solve the model, is that you're going to see a text file that looks like this that you can essentially observe, right? Remember, for the most part, it's explicit. You can also run implicit analysis, which is going to give you a different text file that we're not going to talk about in this webinar per se. Okay. All right. And then once all of that is done, right, you're going to have essentially a result file, which obviously there's a lot of things you can probe. But all I did here is that, I don't know if you can see, the ball starts, hits the floor, compresses, then bounce back. And this is the air back pressure over time, right? So you start with some inflation pressure, it's gonna shoot up, and it's gonna come back down until it equilibrates. And you see this little wave right here is when it damps out the waving, the internal pressure, until it reaches the equilibrium state, right? And then if I look at the next one, I have 5 ball with different inflation pressure. The higher inflation pressure is going to bounce back a little bit more. The lower inflation pressure is going to bounce back a little bit less, as you would expect, right? And that's really the process for setting up a pretty simple model, right? Is that it's always about what's in the preprocessor and what's in the input deck. And as you get more proficient with the tool, as an introduction, right? I couldn't stress this enough, is that you want to build a connection in your mind between what's in your preprocessor and what's in the input deck, right? The more you are proficient with that, the better you are with the tool. And that's really what's required as an engineer, I think, to get proficient with the tool, is to start building that connections. And then, of course, to read the documentations. I think for the engineers on the call, right? I think a lot of you will appreciate the fact that learning is about reading and practice, reading and practice, and reading and practice. And that's really our job, is to be technically proficient in what we do and to add value by the leveraging physics and leveraging numerical methods, right? And that's really what our job is. So really, no matter how complicated a model is, right, the key is to managing the purpose, behavior, interaction, and the nuances of the keywords, right? So when we talk about doing a workflow for Dyna, right, what's the takeaway? Again, is how do you build that connection, right? Because any model becomes simple as soon as you can decompose, you can start building this connection. Because for any challenge, any difficulty you run into, you can look up what's wrong and fix it, right? Because you are building that connection. You're not assuming how it behaves. You can look up the documentations to figure out why it's not behaving the way you intended for it to behave, and then you can fix it, right? Okay, so that's really a quick demo, right? And then hopefully you're not too bored at this point, right? Hopefully you get a sense of what you will have to do to get into the tool, right? But what I also wanted to draw your attention to is some applications, right? Because this is where really the fun begins, is that you're not just looking at these boring key cards all day, right? That's not what the tool is, right? The tool is, once you master it, the amount of application that you can manage, right, in explicit, in implicit, in thermal, in electromagnetic, in fluids, and in their multi-physics interactions, right, is so beyond what I think one person can manage in a lifetime, right? It's really cool in my mind to be able to do so much with a single code, right? Because I don't have to switch to different package when I want to do something else. I can really just stay here and do it, and it has a demonstrated success in a lot of different areas, right? So I want to show you guys a couple really simple examples. I think I prepared 5 or 6 in the next 20 minutes. I'm gonna go over them. So very, very quick, right? And remember, these are not like a patented product. These are me using a CAD package, drawing it up to show you what it is, right? It's literally, I created these. They're not manufacturable even in some sense. Okay, but treat them as an example, as a demonstration of modeling technique, and also a demonstration of what's possible. Okay, so in the first example, I have a fan. This fan is essentially rotating. You mentioned there's a ceiling here, right? I'm gonna rotate this fan at 400 RPM, right? And now I have a soccer ball here. Now it's not really a soccer ball because I'm lazy enough to use the same same rubber ball model I used earlier, right? I'm just gonna use that rubber ball, and then I'm gonna impact that rubber ball against the fan. And then I'm gonna ask the question, what do you think is the stress on the fan as this rubber ball hits the fan while the ball is traveling at 1,000 inches per second and the fan is rotating at 400 RPM per second? Like, what's gonna happen to the fan when I do that, right? I have no idea, but that's like seemed like a very interesting question to ask with the tool, right? So basic setup, I'm gonna go over real quick. I really don't want to get into like how to exactly do it, right? But basically, I have a bunch of contact, which is gonna bond the different body of the fan together, right? Because these fans have individual blades which are slightly angled and they have different connection with the centerpiece that I created. I'm just gonna bond them together for the most part. And remember, these translate to some contact cards. I have a frictional body here, which is between the surface of the ball and the bottom surface of the fan blade, right? Because I want that to be a sliding interface. Therefore, it's a frictional contact. Pretty simple, right? I'm going to have some initial conditions, right? Which means I'm going to start the analysis with the fan rotating at 400 RPM. And then I'm going to start the analysis with the ball traveling at 1,000 inches per second in this orientation here with this coordinate system that I created here, right? Pretty simple to understand. Now, remember, when you have an initial condition, you have to do what's called a dynamic relaxation again, right? That's what I introduced earlier, if you remember. And that's basically my preload. So I preload my structure before I do the actual impact analysis. Okay, that's really what these steps are. And then let's look at the result. Again, I'm going this super fast. We're really not talking about how to do it per se exactly, right? But we're just introducing the basic step. So you can sort of, this is a deformation plot of the fan against the ball. This is the stress plot. Now, I don't have much information about contour, but you can sort of see that that makes sense, right? This is essentially like a beam. The highest stress point right there showing is around the connection point between the fan blade and the centerpiece, right? And this is the deformation plot, right? So with something like this, with enough investigation into the input parameter, into my material, into my inflation pressure of my ball, into the mass of my ball, I can start building a meaningful model to investigate, is my fan strong enough to handle this kind of perturbations, right? What's the connection here? What happens if I make my fan blade longer? Is that going to create a stress problem around my fan blade, right? And what happens if the fans start rotating even faster, right? What happens if I change the angle of my fan blade? These are all the questions we are starting to be able to answer very quickly, right? Once you construct a baseline model that capture the basic input behavior, capture the basic behavior and the input parameter of the components of the model, such as, what are the fan made of, what are the connection points, what are the mass of the ball, what is the inflation pressure of the ball. These are the things, once you capture it, we can start asking a lot of different questions, right? Okay, that's the first example. Second one, right? So in this case, I'm gonna do a quick ballistic analysis, right? And remember, I have a steel plate, a copper bullet. Literally, I don't even have a core that's steel. I have a core that's made of copper. Okay, because all I had was a copper material for a simplified simplified Johnson Cook material model. So I didn't want to make up a steel material model. I want to use something I do have, right? Then I want to see the bullet shatter because I know a copper bullet against a hardened steel plate is gonna shatter, right? And the way to do this is actually not with an FEA method. It's also do what's called a structural aperture Lagrange Eulerian model, right? Basically, what this means is that the structural side, the Lagrangian side, is the steel plate, and that's essentially still done with the finite element, right? But the bullet is actually behave more like a fluid at such a high impact velocity, right? So what you want to do with a model like this is that you want to treat the bullet projectile as essentially like a fluid, right? And the way you do that is to create what's called an SALE domain, right? Which is like this little box right here. And this little box is going to have a SALE mesh assigned to it. And that essentially acts like your control volume, which means as the bullet deforms, right, its behavior is going to be dictated within that control volume, because you're looking at it in a Eulerian frame of reference as opposed to just a Lagrangian frame of reference, like you typically do in an FEA analysis, right? And then once you do that, what we also want to do is to sort of define the behavior, the contact behavior between the fluid part or the Eulerian part against the Lagrangian part, which is a steel plate, right? So this coupling object right here creates a constrained Lagrangian solid method, right? I'm sorry, key card, and that's going to essentially make sure that my projectile parts and my steel plate part, the center piece right there, is going to see each other as a contact pair, right? Which means as the bullet shatters, right, it's gonna see the steel plate and not be able to penetrate it. Okay, and then once you do that, very simple. You can sort of see this is the simulation side, right? You can sort of see it shatters, and you can sort of see this right here. That's the limit of your control volume. Is where I could have made the control volume bigger, in which you don't see this. I probably should have done that, but for the sake of demonstration, I can sort of show you what happens. And this is what happens with a YouTube video of a bullet shatters. You know, not exactly the same. Remember, they have a steel core inside here. This bullet shape obviously is also different, right? But the idea within a modeling approach is, you know, you want to do projectile analysis, really like, you know, getting the material model right and getting the behavior right might be the challenge, might be more expensive in terms of investments, right? But the modeling approach is exceedingly easy to understand, right? As a simulation guy, you want to capture the way you want to do it. It's really not that hard to do. But the key things that you gotta make sure you capture the internal material behavior correctly. Right? In this case, I use more of a dummy copper material, which is why the behavior is a little bit different. And that's the basics of a ballistic analysis, right? All right, next one, let's look at a couple more, right? In this case, I have a lower speed penetration problem. But in this case, right, I don't want the projectile to shatter. I want the plate to be penetrated, right? So in which case, if the bullet is going to penetrate the plate, what happens, right? And in this case, I have to switch around the method of simulation a little bit to treat the plate portion of the geometry a little bit different. And then what I'm gonna do is what's called SPG, a smooth particle Galerkin method, right? So instead of treating this little gray part as finite element, I'm gonna treat it as smooth particle, as like an element-free way of looking at it, right? And then the way to really do that is that the material model, the section cards, which are defining essentially the nature of the formulations, right, of the behaviors, and then the equation of state. These three things are going to be assigned to the centerpiece, which tells that centerpiece how it's going to deform in the presence of external load, right? And it's going to perform a lot more in an element-free method. And I will show you what happens if we don't do that in a bit as well, right? So basically these three cards, which are assigned to this object to define its behavior, is going to tell us how the program, how this thing is going to deform, right? I'm going to create a node set here. I'm using that node set of a 100, right? This ID right here. I'm going to tell the penetrator, which is the yellow piece, and this bunch of nodes right here, that they're going to see each other as contact pair, right? That's the logic, right? So the nodes in the highlighted area is going to see the penetrator in this contact card right here. So you can sort of see the way I'm setting up the problem really is that, you know, I'm defining the characteristic of my plate, then I'm defining the contact between the penetrator and the plate, just like you would do with anything else. But in this case, I'm focusing my energy on the correct cards I want to use to define the correct behavior, right? So this card right here, this contact card, is going to set these nodes against these surfaces on this yellow part, and they are going to see each other as a contact pair, right? Because remember, this is not a simple mesh against mesh contact anymore, right? This is more about particles contacting surfaces, right? And I have to define it in a specific way using this method right here, right? And then this is actually modeled with SPG instead of within elements. So what happens, right? So if you look at here, this is the element-free method, right? You can sort of see as the penetrator goes through against the plate, you can sort of see this is a much more clear way of where the deformation, where the fracture happens within the plate, right? You can sort of expect this to happen. But if you don't do it this way, if you just do it with the basic method of a FEA method, right, you can see this element just erodes, right, where the element basically just magically goes away, right? So why is this not a good way of doing this, right? Is because you are essentially losing the conservation of momentum, right? You can't have mass just disappear from the model. You want to be able to capture its effect after fracture occurs, right? So with the correct material model, this method allows you to really capture the reaction forces of your penetrator as it hits the plate, and can really capture the damage behavior much more closely, right? So this is a great way of doing penetrations, right? Any kind of penetration problems that require a good capture of damage, you can use this SPG method, right? Of course, get a better mature model, get it a better behavior, check your input parameter to get a really good model. But the basic modeling approach is essentially as I've demonstrated. Okay, a couple more, right? Okay, so this is a drop of a large electronic appliance. I'm gonna go through these real quick. This is a 2.7 radian per second angle drop, right, against the floor, basically. All something like this that you have to do, right, is build a contact. Right? So all these joints and contact. By the way, I borrowed this model from Ansys because I can't show you guys our customer model, and for something this large, I couldn't create it myself, right? So, but basically, all you have to do for something like this, is you build a contact to construct the entire assembly for the structure, right, to make sure everything's connected correctly. Any kind of bolted connection, you want to apply a bolt preload, and then you want to apply a rigid wall on the bottom. So you can sort of think of, yeah, the model like something like this could be pretty difficult to build, right? But really, you are just building contacts together, and then you're doing your preloads, and then you're making sure your floor is correctly set up. Then you set your initial conditions. Then you can basically drop a large appliance like this inside Dyna pretty easily, right? So you can sort of see something like this. You can see the stress as it goes through the drop. You can actually just something like energy is something you always want to check, right, in an explicit analysis. So that in this case, they're check the energy for the problem, right? So replace this with any large appliances that you might be working on. We can certainly help you do a drop study pretty quickly, right? Because something like this, right, when you have a 3, 4, 5 ton structure under some kind of drop conditions, right, there are always a risk that you want to mitigate. And an explicit package like Dyna can do this extremely quickly, right? Where it's so proficient at doing something like this that it's so much faster than a lot of the competitive packages as well, right? And then with the Workbench LS Dyna, setting up a large model with thousands of pairs of contact becomes really, really easy to do. Okay. All right, a couple more, 2 more. I promise, almost done. 2 more, right? I want to show you so many things I wanted to show in this webinar. Like I'm almost giving myself too much to present, but 2 more to go through, right? This is a burst rack model. So I have a very simple turbine structure, right? I basically created with nothing but these shell bodies, right? Then this is the burst rack shape. Now burst rack shape, if you're not familiar with, these are like a well-established modeling methods, right? So for different applications, the aerospace working group presented different burst rack shape that one can use. You essentially model these with like water, right? And then you're gonna hit them against your structure. Depends on what kind of structure it is. In this case, it's a turbine. So I just model something very similar to this, and I use it for the demonstration purposes, right? Now, for something like this, you're gonna have to use something called SPH, right? Which is essentially is also another way of doing particles, right? So you're not really modeling the burr shape with elements, you're modeling with particles like this, right? And this particle, if you remember everything we just talked about, right, is going to have a contact defined between the particle and the blade, which is what we're doing here. We're going to define a set for the nodes. We're going to define a set for the bodies, and then we're going to define a contact between the nodes and the bodies, which is really the essence of what it is, right? So this contact card is going to look for set ID 102 and set ID 101. 102 is my nodes, 101 is my body, right? And that's going to tell the program that these little water particles, right, is going to hit against the blade bodies, and then we're going to see what happens with it. Now, before I do that, I'm also going to define the contact between the individual components of my blade and of my turbine. So in case they break, I want to be able to see their contact to each other, right? So that's really what this body interaction object is. It creates what's called a single surface group contact. So this 101 set ID is going to basically include everything that's highlighted in blue right here, and that's going to create a self contact condition. Basically, any portion of anything that's highlighted in blue can see each other as a contact pair. That's really what these body interaction would translate to a single surface contact is. It's essentially a blade set. Okay. And then lastly, I'm going to define the failure condition of my turbine blade, which means that, at what strain, plastic strain value or effective strain value is my blade going to essentially get close to the area where it's going to fracture and break apart, right? So a way to simplify this kind of deformation of damage is to use what's called a mat add erosion. This is essentially a card in Dyna that allows you to define at 15% effective plastic strain and 5% principal strain, right? Tensile principal strain is going to cause the turbine blade to break, which means any area where you see enough strain, right, the element itself will erode, and you're going to see something like this, right? The water particle will break apart once it hits the turbine blade, and in the area where it directly hits, you're going to see fracture that happens, right? So in quick summary, something like this looks pretty cool, right? But really all we did is we created a shape. We're going to call that shape a particle shape. We're going to define the contact between the particle shape and my turbine blade. We're going to define the contact between the body of my turbine blade. Then we're going to define the failure criteria for the turbine blade. Then bam, I have pretty much a model ready to go. Now, of course, I have some initial condition here that I didn't talk about, but that's really the nature of a burst strike analysis, right? And because the burst strike shape and the material model for the burst strike shape is a well-published information that we can use for a much more complicated turbine shape, right? This turbine shape is made up, but we can do this kind of analysis for anything that's much more complicated in real life, right? Because the process isn't really changing. What is changing is the nature of the input parameter. Like we need to understand the structure, its stiffness, the material we're using, the way it's built together. But the process of building it, of building a model, the modeling approach is the same as a simple model that I'm showing you here. Okay. And the very last thing I will show you guys, right? Hopefully you're not too bored, right? Is that if you ever seen those drone capture device out there where people are building these nets to capture drones, right? Obviously, I can't do something that complicated on the fly in a CAD program myself. So what I did was I built a tennis net. I'm sorry, a volleyball net. I look up some basic dimension of a volleyball net. I look up the basic preload they use, right? And then I'm gonna create a situation in which I'm gonna ask the question, at what point does the volleyball go over the net versus being stopped by the net, right? So if you can imagine a volleyball hitting the net, why did it sometimes go over? Why did it sometimes being stopped, right? That's the question I'm gonna try to ask myself by running a simulation in Dyna. Okay, so pretty simple structure, something like this, right? Basically, the ball is still a rubber ball. Pretty simple because I want to use the same thing I've already used, right? So same rubber ball assigned to the volleyball. These beams right here are basically just the nets, right? These nets right here are basically I gave it some kind of plastic material because I technically it's some kind of fabric, right? So you can sort of look at exactly how those volleyball net are made. I won't dig too much into it, so I just did some very quick plastic material I have in my database. The posts, which are these right here, I use a 420 steel because I want these to be really stiff, right, as they should be. And these are solid big posts in real life. Now, these preload, right? So these nets are not just sitting there. If you know, like there are usually pulleys around the post on the left and right hand side, which is going to add a lot of preload to stretch the net and to pre-tension it, right? So I want to model that pre-tension behavior by basically doing both preloads. Even though they're called both preloads, all I'm doing here is I'm creating a beam between this point and that point, right? And then I'm gonna tension it. Basically create a preload tension in the presence of by utilizing a beam model, a beam object in between this point right here and this point right here. And these both preload is basically just me preloading 1, 2, 3, and 4, and that's gonna stretch the net in the beginning before the volleyball hits, right? And that's basically my dynamic relaxation. I'm gonna preload it, which allows my net to behave more like a volleyball net, right? And then lastly, I'm going to create my initial condition in which my ball is going to be inflated and then it's going to hit against the net at 1,000 inches per second, some number I made up, right? Something pretty close. Okay, so you can sort of see at the very beginning, right? So before I do go over too much, you can sort of see this is the post here, this is the post here. You can see the net, this is the total deformation plot, right? The net is being stretched on the left-hand side, being stretched on the right-hand side. It tells me it's pre-tensioned. Right, and then as the volleyball hits it, it's going to stretch and then bounce the ball back. Now you might say, I think this net is probably a little bit too elastic. I would say because I use plastic as opposed to actual fabric material, and maybe my beam is a little bit different. But remember, I drew this basically with like 10 minutes, right? I'm not trying to actually create a volleyball net. But that's the approach, right? If I get an actual volleyball net, I can do the same analysis with an actual geometry, right? With somebody who's actually designing this. Right, no, I didn't go over. Now, what happens if I make the volleyball 2 inches higher above the net, right? You can sort of see that the volleyball will actually go over. And that's an interesting behavior to think about, because this is very similar to any kind of like net capture device that we will do, right? Is that you essentially have a cable pretension system that you want to be able to capture the stiffness and the contact behavior correctly. And that's the entire nature of any kind of net capture device model, right? Which is the same thing as a volleyball model, a volleyball net model, because we're trying to do the pretension correctly and we're trying to capture the net stiffness correctly. Then we're trying to capture the contact between the projectile, whether or not it be a drone or a ball, against the net. Once you capture those elements of the model correctly, we can correctly capture the entire physical behavior. Okay, a lot of information for you guys, right? But basically, Dyna is the go-to thing for explicit, but it has such a wide range of capability inside, say, for example, implicit, doing modal analysis, doing response spectrum, doing vibrations, doing thermal, right? You really want to look at investment in Dyna as more than just doing things that's like crashing a car, right? You really want to look at it as a much bigger investment into expanding the simulation capability that really doesn't exist within a lot of other code that you might have access to, including, say, for example, Ansys Mechanical, which is the default implicit mechanical package that we have. And know that the pre-processor and the post-processor, right? People can use product that's not within Ansys, but consider the Workbench LS Dyna as the one that we offer. I think this is going to be the future preprocessor everybody wants to use, because it's developed by the people who own Dyna now. Okay, that will be the end of my presentations. Thank you.
All right, thanks, Dennis. And just as a reminder to everybody, everything's being recorded and we're going to send it out to you here in the next couple of days. And if you have any questions, we do have a few questions here. Feel free to type them in at this time, and we're going to give you a few moments to do so. And just as a kind of a final closing statement, as an Ansys Elite channel partner, we can help get you set up with LS Dyna and make sure you have the right tools to do your simulations, as well as we have a full consulting team in-house, including Dennis. So even if you don't have Dyna, or you're looking for other options, or you want some help from one of our team members, we would be more than happy to help you there. But other than that, Dennis, I will start asking you the questions. You good?
Sure. Yeah, go ahead.
Perfect. All right, the first one I have is from David. Can Ansys LS Dyna take advantage of system symmetries?
Yes, it can. So you can actually insert symmetry object. It will actually get transferred to what's called an SBC card in Dyna, but it basically behaves like you would expect a symmetry condition to behave.
Perfect. And just so everyone knows, we'll stick around for a few more minutes. I know it's getting close to the hour here, but we have quite a few questions that came in. So next one I have here, let's see, it's from Ben. I'm using LS Dyna now. Most of my experience is within implicit FEA like Ansys and Abacus. Explicit simulations show stress waves propagating quickly through the solid. How do you ensure you get mesh convergence in the explicit explicit solve?
Convergence doesn't apply to explicit methods, right? So hopefully you understand that. So when we talk about convergence, it's purely a artifact of the implicit method, where you have to check for convergence within each step, within each substep of your analysis. Explicit is essentially propagating through the step of your analysis very quickly with a very small time step, with a condition such that you need to get within a small enough of a time step to remain stable. And this is one of those questions that's more around the foundational understanding of the difference between implicit and explicit. Now, Dyna, if you can also do it as an implicit analysis, which will also require you to check for convergence. But key things to remember is that if you are doing an explicit analysis, it's not about convergence. You don't have to check for that. That's why you do explicit, really, is that because you don't have to check for convergence. There's a lot of benefit because of that. The downside is, you have to pay attention to the size of your element. the size of your time step, and also what's the duration of your entire run, and the explicit analysis are limited by those factors.
Perfect. Okay, we have a few more here. So this one's from Hong. How to check keycards in the GUI. Can we modify the inputs in keycards?
Yeah, so good question. So you cannot modify the keycards directly within a preprocessor, right? Remember the idea of a preprocessor, whether I use HyperMesh or FeedMap or Workbench LS Dyna, right? Is that you're essentially creating objects like GUI, right? Things that you can insert, click on, all that stuff. The keycards are what's generated into a text file. Now you can edit the text file after you write the input deck from your preprocessor, right? You can certainly do that. But the preprocessor is always about creating objects in a graphic user interface in which you will have an equivalent input deck that's being written at the end, right? So remember, editing input deck, you do that within a text file environment, not within the GUI itself, right? That's contradictory in a sense.
Perfect. Let's see here. We have a couple more. This one's from Brian. Can you generate one mesh that you use in both Ansys implicit and Dyna explicit analysis?
Yes, you can. It's not entirely recommended. This is a little trickier question. So the basic idea here is that any mesh you generate, right, can be used for whatever solver you want to send it to, right? So Ansys implicit mechanical uses the APDL solver, as I'm sure you understand, right? Workbench LS Dyna uses the LS Dyna solver, right? So you can send the same mesh body to those two solvers, but what you want to pay attention to is things like element formulations, right? The element order. These are the things that are different between, like, they have different requirements between Ansys implicit and LS Dyna, right? Because LS Dyna is going to require you to have a different. You actually can define like section informations inside LS Dyna. That doesn't make any sense for APDL solver, right? So pay attention to the element formulation, element order, right? Section informations. These are the things that need to change between given whichever solver you're sending into. But the mesh body, right, is interchangeable, right? You can use it for whatever reason you want to use it. That makes sense, hopefully. Yeah.
Perfect. Dennis, there's a ton more that are coming in. So do you have a few more minutes?
Yeah, I have time.
Okay.
Go ahead. Yeah.
Perfect. We'll hang around for like another 5-10 minutes. And then just so everybody knows, we will, I'm going to take all these questions and if we don't get to it, we will have someone reach out to you and make sure that we follow up with you.
Yeah,
So,
sure. Go ahead.
Let's see here. This one is from Feng. Hi, Dennis. Could you please tell me what's the termination of your fan ball impact model?
Fan ball. Which one is that?
The one with the
this one right here.
Yeah, the first one with the rubber ball and the fan, I think.
What's the termination? You mean like the termination time? Is that what you mean?
It just says, could you please tell me what's the termination of your fan ball impact model?
I'm not sure exactly I understand what that means. I think this thing runs for like 0.2 seconds, if that's what you're trying to ask. Basically, I let the fan rotate for I think 0.2 or 0.5 seconds. I think that's what I did. I don't remember honestly. The control termination might be what he's trying to look for. Usually that tells you how long the model ran.
Okay.
Maybe that answers your question. Ask a follow-up question if that doesn't answer your question. Okay, I can try to answer.
Perfect. Let's see here. Another one from Daniel. Building off the previous question, what exactly is the difference between explicit and implicit solvers?
Well, implicit problems require usually are ones that runs longer, require you you can really run with as large of a time set as you want. Explicit analysis are limited by, for example, the size of your element, essentially the speed in which sound travels through your material, right? So that limits the time step that you have. But the benefit of an explicit analysis is that you don't have to check for convergence. That's usually a good way to look at it, right? It's essentially a different way to propagate through the state of a system, right? So if you have a model that takes a long time to run, for example, the physical event takes a long time to proceed, you usually have to approach that problem with an implicit method because the duration of the physical event is very long. If you have an impact event, right, the duration of the impact event is usually in the order of microseconds. And those type of problems are usually also one in which includes large deformations, right? In these cases, right, it's much more suited for an explicit analysis, because in explicit analysis you don't have to check for convergence, and you can propagate through analysis much faster. So really the difference between the two, it's about the nature of the problem, like how linear and nonlinear it is, and what's the duration of the physical event, and that usually dictates whether or not you want to approach a problem implicitly or explicitly, right? Hopefully that answers your question. The answer to that can get much deeper, right? I don't know if you're looking for even deeper answer to that. These becomes more and more of a textbook question once you get deeper and deeper than that. Hopefully that answers your question.
Yeah, we have we have a ton more here, so
All right,
we'll
keep
go.
going. That's fine.
Okay, we'll go for another 5 or so minutes here for everybody. We have one from Khaled. Thank you for the informative presentation. I was wondering if it is possible to establish a connection between LS Dyna and Ansys APDL in a manner similar to the integration provided by Ansys Workbench.
Wait, sorry, say it again. Establish a connection between what?
LS Dyna and Ansys APDL in a manner. Okay.
In a manner what? In a manner what? Say it again.
Oh, sorry. In a manner similar to how the integration is provided with Workbench.
Okay, so I guess this confusion here is this, right? So the Ansys Workbench LS Dyna environment, which is this thing I'm showing you on the screen. If you can see me, you see this thing I'm showing you on the screen, right? That's the preprocessor used to write an input deck, which is a K file that look like this. I don't know if you can see on my screen right here, right? And that's a input deck that's only going to be used for LS Dyna solver. The APDL solver requires a different format of input. Like it's actually a DAT file contain a bunch of APDL codes. If you ever look at, like, if you ever run an Ansys mechanical model, right, and you look at exactly what it's writing out, it's writing out a DAT file, .dat file, and that's actually completely different. So Workbench LS Dyna does not have anything to do with APDL solver, right? They are completely different things. Hopefully that answers your question. Yeah.
All right, let's see. We have one from Matlock. Says, excellent presentation. How do you ensure sufficient gap between objects when you are defining initial velocity on an object before impact so the time is not wasted?
Oh, good question. I mean, this is really about geometry preparations, right? So you want to make sure you maybe leave a little bit of a gap. That may not be a bad idea, because sometimes you might have initial penetrations due to the nature of the model setup, right? But that's really all you have to do, is to make sure you have a very small amount of gap, such that only the first few cycles within your explicit analysis is going to have no contact, and the rest of it is going to just impact. So to answer your question, I guess in simple terms, let's just make sure you, do your geometry prep correctly. I think that's gonna mostly do it. Hopefully that answers your question. Just geometry prep really is where you want to do it. Yeah.
So this one we might have to follow up on for David. Are there any examples of aeroacoustic problems available? And I'm assuming like within the sample models.
Yeah, I do not know much about aeroacoustics, but please follow up with that. We'll find people who have the answer for you. I myself, I do not know much about it, so unfortunately, I'm probably not much help in that regard. Yeah.
Perfect. Let's see here. Why? Okay, this one's really good. I think why would I use Ansys LS Dyna over mechanical?
So remember, right? When you or your organization have simulation capability, right? Ansys Mechanical is mostly, or I should say entirely, an implicit code, right? So Ansys Mechanical, so if you buy the Ansys Mechanical, say for example, enterprise or premium license, right, you do get an explicit dynamics package, but LS Dyna is a far better and honestly a far more developed explicit code, right? So why do you need an explicit code? Is that because there are problems you simply cannot do inside implicit. So one of the gentlemen earlier asked, what is the difference between implicit and explicit, right? So imagine you have a problem that that's very, very short in duration, like impact, but also have extremely large deformation. So you really cannot do that kind of problem inside Ansys Mechanical, right? And that's where you need an explicit code. It doesn't have to be Dyna, but you're gonna need it. Now, some company may not need to do these highly transient situations. Then you might make an argument that you do not need Dyna. But remember, the key point I want you guys to take away from the presentation, right, is that LS Dyna is also a highly capable implicit code, right? So you can use Dyna to do all of it, but you can only use something like Ansys Mechanical to do implicit, right? So that's why you want to look at Dyna as a potential package, because not only can it allow you to do things you can currently do, it can also allow you to do things that you can do, but do it even better in some situations. So hopefully that
Perfect.
answers the question. Yeah.
Great. And then looks like we have a couple just saying excellent presentation. Thanks, Dennis, from a couple people here. And then just one final one here. We have a question from someone that came in that's I have a consumer product my team is working on, but we don't have Ansys or any other simulation software. How can Rand in your team help?
Reach out to us. I feel like, if we could, set up a call to understand what you guys are working on, like what is the challenge you're trying to overcome, right? I feel like we can certainly help you look at, in two ways. One is we can look at the specific program to see if our team can help you using simulation tool that we do have to solve that problem for you, right? I think simulation is always about, studying the physics behind whatever it is you are working on, right? So we really offer the service to understand the physics by using these tools with you and for you to see if we can find answers that you may or may not have seen. That's the first way. I think the second way is, we might be able to introduce the simulation into your organization through this initial collaboration, right? Sort of to give you guys a window into, if you have a problem like this, how can simulation help you, right? We want to sort of answer that question for you through this collaboration, right? So I think the first step, please reach out to us. I think there are people on the team, more suited on the sales and marketing side than myself, to answer that question even better. But hopefully that answers your question.
Perfect. All right. So just for everyone, thanks for joining us today. We did get a couple more questions, but we're going to just wrap things up and we'll reach out to everyone here in a follow-up that did ask a question today. And thank you, Dennis, and everyone for joining us. And I hope you have a great rest of your day.
Thank you.
Yeah, thank you.